Charlie, and I'm here to talk about squirrels. But first, a bit of crypto history. How did crypto work back in the days? Some smart-looking people said they had a new cool crypto system. Other smart-looking people would look at it and then say, yeah, it's definitely secure. And then other people would break it. Then, the year 1982 came, and with it, the seminal paper by Goldwasser and Micheli. It gave the first provably secure crypto system. Since then, it was decided that we want formal proofs of security, and this was born modern cryptography. So, what has been happening since? Starting from then, smart people came up with a new crypto proof. Other smart people looked at the proof and said, yeah, it's definitely correct. And then other people broke the proof. Wait, let me be clear, we of course need crypto proofs and not all of them are broken. But I will use the word of some famous people to tell you what is the issue. 20 years ago, Bernard and Rogoway said that our field may be approaching a crisis of rigor. Around the same time, Shayalvi said, do we have a problem with cryptographic proofs? Yes, we do. On my side, to be honest, when I do a pen and paper proofs of a complex crypto system that is around 40-50 pages, I don't know, I am not able to tell with confidence that my proof is correct. And when you have to review a paper with 50 pages of proof in the appendix, meh. So what now? Computer-aided cryptography was proposed as a solution in 2005. And you know what is crazy? It worked. Many successful tools with real-world impact have been developed. Among them, EasyCrypt, CryptoVerif, Tamarin. As you can see, we have many tools. So guess what we did? A new tool. Okay, wait. There is a good reason for that. And it's not just because I love squirrels. We strongly believe that compared to all those tools, a novel and different approach was needed. But to tell you why, I first need to give a bit more details about the formal models used to make cryptographic proofs. I'm first going to talk about the two main models used for cryptographic proofs, the symbolic model and the computational model. Then I'll tell you about the foundations of our approach, the BC logic. And finally, I'll give you a taste of our tool, the squirrel prover. The two main models for proving security are the computational and the symbolic model. The first big difference between the two models is how to model the attacker. In the symbolic model, the attacker has a fixed set of capabilities that he may combine however he wants. Kind of like a Swiss Army knife. In the computational model, the attacker can do almost anything, like MacGyver. In a bit more details, in the computational model, the attacker is essentially any program executable in reasonable time. And we just assume that some computational problems, like integer factoring, are hard for those attackers. Essentially, the attacker is anybody with a computer and like 5 years of execution time. In the symbolic model, the attacker can only perform a combination of a fixed set of capabilities, and the primitives are essentially assumed secure. On one side, we get strong guarantees with few automation, while on the other, we get weaker guarantees with a lot of automation. Both approaches are interesting, and it is very unlikely, for instance, that we will ever reach in the computational model the level of automation of the symbolic one. The second big difference between the two models is on how we write and reason about protocols. In the computational model, we describe protocols with a low-level and detailed programming language, and we then perform transformations at the level of the code to prove security. In the symbolic model, we describe protocols with a high-level programming language, and we reason over the set of all possible executions of this protocol to show the security. Essentially, one is low-level, and this more precise and expressive, and one is high-level, and this more intuitive and easier to manipulate. Reasoning at the code level or at the execution level. Does it make a big difference? We claim that it does. Reasoning at the code level is harder when you have complex sequences of actions with many interleavings, you have global execution restrictions, like phases, or finally, when you consider security properties that are essentially trace-based. To give an example on the last point, let us look at the unforgeability axiom of a keyed hash function. It is a function that, given a message and a key, allows to authenticate this message to other people. Only somebody with the key can produce the hash of a message with this key. It is unforgeable. This property can be expressed as a property of all possible executions of the protocol. Given a possible execution, whenever you successfully verify a hash, you know that there exists previously, somewhere in the trace, a point where this hash was honestly produced. This property is naturally expressed as a property of the possible executions of the protocol. If you want to express this at the code level, you have to write your assumption as the equivalence between two pieces of code, and then you have to show that your protocol is an instance of one of the two pieces of code. This appears to be less natural. To sum up, we saw that the computational model is more precise and expressive, provides stronger guarantees, but is at a low level of reasoning. The symbolic model is less precise and provides weaker guarantees, but is at a higher level of reasoning, and this has a higher level of automation. Both approaches are complementary, but we claim that there is another path, somewhere in the middle. And so, we ask one big question. Can we get the best of both worlds? Or, to say it clearly, is there a way to reason at a high level and still get strong computational guarantees? In the past decade, a new way to make computational proofs was introduced, the BC logic. It was introduced in 2014 and used and expanded in the years that followed. Essentially, it allows to obtain computational guarantees while reasoning inside a first-order logic. To do so, it provides a way to describe all the possible behaviors of a protocol inside purely syntactic terms that only contain function application and base constants. What is the difference with the classical code-based modeling? On one side, you have explicit sampling. On the other side, sk is a function that takes no argument and gives back a random bit string. We do not assign a variable to an attacker call, we model the attacker using a function symbol. And so on. It has two very interesting properties. Abstraction. We don't see any probabilistic sampling, we don't see any variable assignment, etc., etc. Locality. If we reason about a term, it contains all its probabilistic dependencies. No side effect, no weird states. How to prove protocols in the BC logic? The idea is to fully describe the possible behaviors of the protocol. We just look at a simple protocol. We're using a shared key sk. Alice authenticates a nonce A to Bob, and this by sending the hash of A with sk to Bob. Bob answers OK if the hash is valid. We can describe this protocol using terms by writing down inside the logic the sequence of possible messages seen by the attacker over the network. The first message will simply be the hash of A with sk. Then, the second message is a bit more tricky, as it depends on some attacker input and on a conditional test made by Bob. Is the hash correct? The attacker input is modeled with a dedicated function symbol. And for the conditional, we simply include inside the syntax a ternary function symbol that we denote by if then else. What could we want to prove over this? Well, here we would want some authentication property. So, the condition of Bob succeeds only if the attacker simply forwarded the message. This is written with an implication where the left-hand side is exactly the condition of Bob. To make a statement over this implication, there is in the BC logic an indistinguishability predicate over sequences of terms. We can then express the fact that the implication should be equal or indistinguishable to true with overwhelming probability. And now we want to prove this using the unforgeability axiom. What is interesting is that it becomes completely syntaxic. The honest hashes given to the attacker are the ones appearing inside M0. And the property holds because we only have the one sent out by Alice. So, to sum up, we have terms modeling possible behaviors of the protocol, we have a logical predicate modeling computational indistinguishability, and we can translate classical cryptographic axioms inside of terms, yielding logical axioms. Remark that here, we only get the authentication property for the first possible sequence of messages of the protocol. We would also need to do it for the other one. And of course, we are not limited to reachability properties. To show the computational indistinguishability of two protocols P and Q, we do so by proving that the axioms entail the BC indistinguishability of their possible sequences of terms. That's it, you know the BC logic. Or, well, you have the big ideas so that you can understand the user interface. Making it so that behind the curtains, it actually gives you computational guarantees is quite a pain in the Essentially, you have to see the logic as a first-order logic whose models are probabilistic Turing machines. Okay, let's forget about that. And so that you forgive me, here's the picture of a cute squirrel. So, back to our ships. The BC logic is quite cool, but had two drawbacks. First, it had no mechanization. Second, it only worked for protocols with a fixed number of agents or sessions, because you have to enumerate all the traces. As our contributions, we solved both. We developed a metalogic that allows to reason about unbounded protocols, and we integrated it inside a mechanized prover. We said that in the BC logic, you have for each protocol many sequences of terms, and have to do a proof for each. In the metalogic, we capture all that in a single formula on proof. And this proof can be independent from the number of sessions, and this proves the security of an unbounded number of sessions of a protocol. How does it work? It is because there is, in our metalogic, a quantification over all possible traces at the top level. Phi must be true over all possible traces of the protocol. And of course, to prove that we obtain computational guarantees, we must prove that each metalogic rule matches multiple applications of rules of the BC logic. To sum up, we have a metalogic with rules and axioms that allows to prove either properties over all traces of the protocol or indistinguishability properties. And the main theorem is clear, it gives computational guarantees. The squirrel prover, it looks like this. That's my Alice and Bob protocol, so what does the metalogic formula looks like? Essentially, we have inside the logic what we call macros that can refer to the input, the output, or the condition of an action happening somewhere in the trace. And we can show on our example that if the condition of Bob succeeds, it actually received a value sent by Alice. Squirrel supports classical first-order reasoning rules, but also cryptographic rules like EUF, a nickname for existential unforgettability, that actually matches our intuition. If we have a valid hash, we know that it was honestly produced previously. As only Alice can produce such hashes, it means that there exists an honest session of Alice that produced this message. And we conclude. What did we do with it? Many kinds of proofs based on many kinds of assumptions. We already have proofs for some complex properties or complex protocols. And we can notably leverage a composition result inside our proofs. What do we plan to do with it? Well, look at more complex stateful protocols, maybe some quantum stuff. We don't know the limits yet. Don't forget to check out the code, the paper, videos of cute squirrels, and see you soon.